So what do we talk about the sorting algorithms? First, most important thing is what is the worst case time complexity? Yes, so asymptotically, how good will this perform? So what do we know about these algorithms? What is the worst case time complexity of each?
O of n square for insertion sort.
N square for actually two of these, worst case, right? And O of n log n for all others. Yes, this is what we know. So at some point of time, I said, well, we can't do better than n log n. So question here is fine, n square n log n, but isn't there any algorithm that can do better than this? So that is the big question. Can we do better than O of n log n? Can we do better than O n log n? What do you think?
Sir,
Mhm.
sir, if we know the maximum, like the maximum value which we have to use, then we can use another array to store the elements.
So you are saying, okay, if I have some additional information. So if I have
Yes,
some
sir.
additional information, possibly. But the question is in general case. But what about the general case? So general case means, okay, you are given n elements and they are arbitrary. They can take any value, right? They can take any value. You have no information about that a priori. You have to be ready for whatever input comes to you. Okay, we can take arbitrary values, and your algorithm should be able to handle any arbitrary input of n elements, integers or whatever. Right? So even if we restrict to integer, then also it is not possible to say better than O n log n in the general case. But let's say in general, n elements, arbitrary values, can't do better than O n log n. Why is that? So here there is a catch. So at least can't do better than O n log n. So why? Why? So let's look at our 5 algorithms that we have put on the page. What operation do they depend on for sorting?
Comparison.
Let's look at our sorting algorithms. So you are saying they depend on comparison operation for sorting. So that means my input can be, say, some edit each, my n elements. So my n elements, suppose they are edit each, abstract data type, right? So think of them like black boxes. And you have no idea what they are. The only operation, suppose you can do, suppose the only operation you can do is comparison. So that means all this less than equal to, greater than equal to, greater than. All this is all the operation you can do, and a comparison can give you two things: yes or no. You can compare two elements; it can either give you yes or no. This is what you can do. You have no other information about values. That is the general case. Okay. And what you're saying, I'm depending on comparisons for my sorting. So this we call comparison-based sorting. Now, yeah, you may say, oh, but in AUL sort, we may do some more things like initializing some data structure, moving pointers. Similarly, in heap sort, we may do some other things than comparisons, right? Isn't it? We may do something
Yes,
other
sir.
than comparison also. So that's where the catch. So what it means is that, okay, so let's assume that we only charge for comparisons. So that is, okay, yes, they do some additional operations. Let's not worry about that. We will not even charge. So that means I will only consider how many comparisons they are doing. Let them do some other things. But we only charge for comparisons. So that means we will find out, oh, what is the minimum number of comparisons that are needed. And then whatever you have to do is extra. So if I can identify what is the minimum number of comparisons needed, then I can somehow establish a lower bound. So that means number of comparisons can help establish a lower bound. Because the main operation you are doing is comparison. You are comparing two elements. You see all the algorithms, this is the main thing. Compare the elements, based on that, do something. But again, you keep on comparing the elements. Okay. So this is what comparison-based sorting, and what we want to show that this lower bound is omega n log n. This is the lower bound on comparison-based sorting. You cannot do better than that if you are using a comparison model. That's all. Till now, we have not seen anything better than n log n, so looks okay, I think. But how do we prove this? So we have to prove this. Sure. So how do we start? And what we will do, we will start with something more simpler than sorting. Let us start with searching. What is searching? You are given an array. And elements. And you have a key X. Search X in A. How do you search?
If it is sorted, then we do binary search.
So let's say A is sorted. So suppose it's sorted. So you can sort it. Suppose it's sorted. Sure. And you want to search. So you do something like binary search. In binary search, what is the main operation?
Comparison.
Comparison. So you compare X with some AI. And see, based on yes or no, you do something. You can say yes or no. Binary search, that is the main operation. You compare X with any element, you find either yes or no. In general, if you take any searching, this is what you do. This is what you compare. Now, can we show that binary search, or for searching in comparison model, you cannot do better than what is the lower bound for searching?
Omega log n.
Omega log n. You cannot do better than omega log n in a comparison based model.
Sir,
Yes.
Sir, how we prove this?
Yeah, we will prove this. Yeah, we have not proved this.
Okay. Okay, sir.
So I'm saying, okay, let's first prove for searching and then we will.
Sir, is
generalize
it the
the
lower bound or upper bound in binary search? This log n.
lower bound, lower bound is omega log n. For any possible, see, binary search gives you log n. But suppose you say, oh, I can come up with a better search algorithm based on comparisons that will be better than log n, right? So how do you show that log n is the best you can achieve? You cannot do better than log n for searching in a comparison based model.
Okay, sir.
How do I prove this? Let's take an example. Let's take an example, simple example. I have an array A with 3 elements, A0, A1, A2. And suppose I'm doing binary search. I have X, I want to search X in this array. Okay, how will I start? How will I start my search? Okay, you're not telling, I guess all of you know. This is too trivial to say, so sure. I'll compare X with the middle element, yes. So if X is less than A1, I do some comparisons. I compare X with the middle element, yes. And with this comparison, I may have to answer yes or no. Swaroop, are you saying something?
No, sir, it was by mistake.
Okay. So we compare X with A1. I may have two things. It can either give me a no or it can give me yes. So suppose it gives me yes. What will I do? Or let's say no. If it gives me no, what will I do?
Sir, then X is greater than AI, which means we have to search for the X in the second part of the array.
So that means X is larger than or equal to A1. So then I will search X is less than A2. Is X less than A2? Again, it can have two answers, no and yes. Okay. And similarly, if the answer is yes for this, answer is yes, that means X is less than A1. So then I will compare it with
A0.
A0. Again, this can be either yes or no. Okay, let's see what happens. So if X is less than A2, the answer is no. What does it mean?
X is greater than or equal to A2.
Right? And I can't search anymore. That is my final answer. X is greater than equal to A2. That's my answer. If I go this path. Okay. Let's see what happens if it says yes. What can I say?
That X is greater than equal to A1 and X is less than A2.
Right? That is the answer. No further, I cannot search any further. So now what will happen here? Answer is no. X is less than A0, answer is no. That means
X is greater than or equal to A0 and X is less than A1.
okay, finally. If I do all yes, 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 so then where will I go?
X is less than equal. Easy.
Or I can write here so that this looks good. Right? I cannot do anything else. So I need to have one of these 4 answers. Okay? All possible answers. So we took a very simple example of 3 elements in an sorted array, and we tried a binary search. And we say, okay, if we do not know what the elements are for any arbitrary value, this is how I will proceed. This is how I will proceed. I can go to any path. Okay. Now, so this is something, this is like a binary tree, right? And we can also call it a decision tree because we are taking a decision at every point. A decision tree. Okay. So I have written it for 3 elements. You can generalize that for n elements, right? How many answers will be there for n elements? How many possible answers?
N plus 1.
N plus 1 for n elements. Okay. And yeah, so there will be some intermediate decisions you will have to take. So what does it tell? What does this tree tell? So can we compare this tree with the algorithm? Okay, let's compare decision tree with the algorithm. Okay. So let's take an internal node. Of the decision tree like this. This is internal node, this is internal node. What does it correspond to in my algorithm?
We are still not finished, means we will not return from that point.
Yeah, but this is just a comparison. We are doing a comparison. Yeah, but I agree. Yeah, this means, yeah, you are in between, but each internal node here is a comparison in this tree that I'm showing. That's a comparison, a single comparison operation. One comparison operation. Right? Each node is one comparison operation and it has 2 decisions, yes and no. This that does something. But what is a leaf node?
So conclusion.
Yeah, so I found the answer. I found an answer. Now, what is a root to leaf path? One path. Let's say I take this path or this path. What does that tell?
Sequence of decisions made by the algorithm.
For a particular input. So this is algorithm execution. For a particular input. Right? So for different inputs, you have different paths. For some inputs, you may take this path. For some, you may take this path. So there are different paths for different possible inputs. Now, what is the length of this path?
Log.
What is that?
Log n.
Log n.
No. What does that correspond to in my algorithm?
Number of comparisons.
Number of comparisons, or I can say running time. Because I'm not charging for anything other than comparison. This is the running time. Running time for a particular input maybe. So now let's try the other thing. What is the worst case running?
It would be log n corresponding to the rightmost or leftmost
Sir, it will be the height of the tree.
Sir, you are not audible.
Yeah, Kenny?
Yes, sir.
Yes, sir.
Yes.
Okay,
Yes, sir.
there was a power cut. I don't know if any of you are here in the campus also. So, yeah. Okay, I'll turn off my camera. I'm on hotspot now. Okay. So you can still see my screen?
Yes, sir.
Yes, sir.
Yes.
So yeah, we were saying what is the worst case running time of my algorithm in terms of the decision tree?
The height of the tree?
Height of the tree. What is the longest path for any possible input? Height of the tree. So that means once we have the decision tree created, I can find out the height of the tree, and that will give me the worst case running time of the algorithm in this comparison model. And now it's not very difficult to find out the height of the tree. Okay, so then question is, okay, what is the height of the tree?
Sir,
Yes.
sir, isn't it the every case running time?
So that's a worst case, right? What is the height? How do you define the height of the tree? See, you are assuming, see, for example, let me clarify. I have given you an example for a binary search. Okay, very important. You may do this in a very different way. You may do these things in some other order. Okay, so in general, internal nodes may differ.
Sir, but like every X,
So
there the
sequence, the way
answer
in which you are doing comparison, the sequence may differ.
Sir, like for every X, the answer will be at leaf node only.
Yes, yes. But it will be at one of the leaves. So what is the worst case running time? That will be, what is the longest path you can take in this tree? There is nothing but
Log
longest
n.
path from root to leaf. Yeah, first of all, you have to agree with this, or we can discuss that this is the worst case running time.
Sir,
Because I am finding what is the longest path from root to leaf. Yes.
sir, isn't all the paths are equal?
Yes, sir.
Yeah, that is
Yes,
what I
sir.
will come to. I'll come to that point. I'll come to that point. Right now, do you agree with this? I'll come to that point. Are all the paths equal? In general,
Sir,
do
why
you
don't
agree?
we,
Height of the tree is the longest path from root to the leaf.
sir? Sir, am I audible?
And that is the worst case running time. I think what you're confused with, you're saying, okay, in this case, all the paths will be. Mhm. Mhm.
Sir, why
I
don't
can
we
hear
check
you.
for
Can you hear me?
equality comparison?
Can anyone hear me?
Yes, sir.
Yes, sir, we can hear you, but I think you means you are hearing us after some amount of time, sir.
You can do equality. Okay, there's a lag. Sure. Okay. Got it. Okay. Yeah. So yeah, the question was that why don't we do equality checking? We can do that. I defined 5 kinds of comparisons. Less than, equal to, less than, equal to, right? Greater than, equal to. You are allowed to do all 5 kinds of comparison. So that is where I think I need to mention this. See, this example that I'm giving is for binary search. But if I have to establish lower bound on any type of searching, right? That means my internal nodes might differ. They may not be these. My internal nodes may differ. You may do only say equality checking, like you were saying. You may do some other type of comparison. You may do greater than equal to, whatever. Internal nodes may differ, and the path lengths may be different. Yes, but what will not change? Question is, what will not change in this
First
tree?
case.
What will not change in this tree?
First case.
No. Worst case we will define based on the tree. But in this decision tree, what will not change? Even if you change your algorithm, what will not change?
Sir, the length of
The
route
number of
to
possible
the
outputs.
The number of?
The number of possible outputs.
Very
It's
good. The
yes
number
or
of possible
no.
answers. Yes, no, the number of possible answers will not change. Very important. So see, you can, what I'm saying, you can replace these things with some other algorithm. It doesn't matter. Change it with some other algorithm. Internal node may change, some other comparison. It may happen somewhere you're finding answer here itself. Somewhere you're finding answer even later. Okay? It may happen that answers can be at different labels. But what will not change is that you have to account for all possible n+1 answers for an input of length n. X can be anywhere. Do you agree with that?
Sir, can you explain this again? I didn't get.
You see, your X is arbitrary. X, you have to account for any possible X. X is arbitrary, and you are given these n inputs. A1 to an is given to you, or A0 to an is given to you. But X is arbitrary. X can lie anywhere in the array. So in the general case, you will have all possible n+1 answers are possible, depending on the value of X. Do you agree with that point?
Yes, sir.
That is what I'm saying. So you will have to account for all possible n+1 answers. And what does that mean? That implies number of leaf nodes are n+1. There are n+1 leaf nodes in the tree.
Sir?
Yes.
Sir, what do we mean by internal nodes may differ? Means what is that for? Difference?
That
What
means that instead of doing, say, X is less than A1, you may do X is equal to A1, or X is greater than something. You will have to use comparison system, but you may do different different way. You may use a
Okay.
different way to
So
compare.
means and we are
They will all be
number of leaf
compatible.
nodes is fixed because x can be to the left of a0 and considering all possibilities to the right of an.
Yes, yes.
Okay,
X
okay.
can be anywhere. So that means all possible answers are there. That means whatever way you construct your decision tree, this is a binary tree, you will have n plus 1 leaf nodes. Okay, just a second. I think the power is back. I'll come back to the institute network. Okay, can you hear me?
Yes, sir.
Okay. Okay, so okay, you can see my screen also.
Yes,
Yes,
sir.
sir.
Okay, great, great. Okay, sure. So now, okay, where we are saying yes, we defined a simple input for binary search. We created a decision tree. We found out there will be n plus 1 leaves. And we can just find out the height of the tree to define what is the worst case running time. But then some of you had this apprehension that, but here all the paths are of the same length. So that is where I'm saying, now let's think the general case. Your algorithm may be different than binary search, but what you allowed are again comparisons only. So you may differ. The internally the way you are doing things may differ. You will still do comparisons, yes, at every node. But what will not change is how many different possible answers are there. There will be n plus 1 possible answer as the leaf nodes of this tree. And there will be some internal nodes that are doing comparisons. Now the question is, and each comparison is binary, you get a yes or no answer, right? So that means now you have a binary tree with n plus 1 leaf nodes. What can you say about the height of the binary tree?
Omega log n.
Binary tree with n plus 1 leaf nodes. So what is the height? So we already saw that when we were talking about binary trees. If there are n nodes, height is omega log n. So if there are n plus 1 leaf nodes, of course, height has to be omega log n. Yes, it has to be omega log n. Cannot be better than log n, right? And that means the worst case running time for search in a comparison based model is omega log n, lower bounded by log n. You cannot do better than that in a comparison based model for searching. Good to know. Okay, any questions here? Now let's go to sorting. Let's now go to sorting. What about sorting? So in the searching, each internal node versus sorting. So what was an internal node in searching? Something like this. I compared X with an element. Compared X with an element. What will happen in the case of sorting? Is that too difficult? What will happen in the case of sorting? What will be the internal node? Okay, anybody listening?
Is it not comparison, sir?
Comparison, but what kind of comparison? In searching, we had X less than AI. So in sorting, what will be that?
X less than minimum or maximum.
What is X in searching? In sorting, what is X? In sorting, you are given an elements.
X in searching, X is a key. In sorting, X is the updated minimum or maximum, I think.
No. You again remember your sorting algorithms. What do you do? What is the comparison you do?
Two elements in
AI less than EJ.
Yeah, AI less than AJ. Or something like that. You compare two elements of the input. You compare two elements of the input. You have no other information about the elements. The only think about that, they are like ADTs. You cannot do anything other than comparison. You don't even know, let's say you don't even know the values. You don't care about the values. What you care is that, okay, you can do any of the 5 comparisons and you can get a yes or no answer. That's all you care about. Okay, so in that case, in sorting, you will do this. If AI less than AJ or AI equal to AJ, something like that, you will do comparison that will have yes and no answer. Okay, see in the tree we have 22 things, internal node and leaf nodes. What was the leaf node in the case of searching? It was okay, the final answer was X between some AI, X is greater than AI and less than equal to AI minus 1. Depending on what kind of, if they are sorted in increasing, decreasing order, like one of this. Or it can be the other way around. One of those. So you will have these kind of leaf nodes and there will be n plus 1 such leaf nodes. In sorting, what will be a final answer? You say, okay, now I have found the answer. What will be a final answer?
So some permutation of given.
Some permutation of the n inputs. So it will be some permutation, something like, okay, A1 to AN I have written, so something like A5 is less than equal to A3 less than equal to A7, like that, less than equal to A of 2. So it will give you ordering of the input. A5 is less than or equal to A3. This is the final sorted order. Final sorted order. That will be a leaf node in the case of sorting, right? How many possible leaf nodes for an arbitrary array A?
N factorial.
And factorial, very good. So number of leaf nodes is n factorial. Okay. Everything else I talked about remains the same. So let me show you the figure once more. So what will happen in the case of sorting? Each internal node will be comparing two elements. AI less than AJ. Similarly here, you will compare some two elements of the array. And you will do some execution. And finally, you will arrive at an answer. An answer will be one of these n factorial permutations. And for an arbitrary input, all n factorial are possible. So you have to account for all n factorial possible leaf nodes. And everything else applies. So even if your algorithm changes from insertion sort to heap sort to AVL sort, you will do some other things in comparison, but at least the comparisons have to be done, right? Because that's what they use. And final answer has to be obtained as the final sorted order. So that means, so what is the worst case running time? For a sorting algorithm in comparison based model.
Sir, log of n factorial.
Yes, so this will be omega log n factorial. And what is that? I think we have done that during heaps. What is that?
N log n.
That is nothing but omega n log n. When we have log n factorial, we said we can write in both. We can write it as, right? We said we can do it omega n log n and also theta n log n. But here we are trying to find a lower bound, right? So we can say this is omega n log n. Yeah, the height will be at least log n factorial. We know log n factorial is lower bounded by n log n. So good. Omega n log n. That's all. So that means for a comparison based model, if you're doing a sorting algorithm, O n log n is the best you can achieve. And be happy with that. Be happy with that. And that also means if you have to do better than O n log n, you have to go beyond comparison. So you have to go for a model that does not use comparison as the main idea. Okay. So to do better than n log n, you have to use more information. You cannot treat them as black boxes and just compare. No, more information. So what kind of more information we can use that these 5 algorithms are not using, you think can be helpful for sorting faster? So let's say, okay, and this can only be done in a very restricted case, in some restricted cases. You can do it. So let's talk about integer sorting. So you're sorting only integers. You're sorting only integers. What is the other information you can use? You have n elements, unsorted. You have to sort them. So you want to do something more than comparison. What is the extra information you can use? Yes, any answer?
So there cannot be one integer between two consecutive integers.
So see, till now we are not using things like, oh, what is the range of values? That means what is the minimum, what is the maximum? I can use that. And maybe that can help me to define a better or more efficient sorting algorithm in the cases where some property about range holds true. So I can use the range of values. They range from, see, suppose you are given that there are n integers. I'm just giving an example. In range 0 to 1000. They will not go beyond this range. What kind of algorithm you can think of that will be faster than n log n? Very simple algorithm. Can you think?
Sir, the integers are means repeating or non-repeating.
They can repeat. They can repeat.
Okay. So, sir, we will form another array of the size 100, 1000, and then we will store the means a of the value is equal to 1 or 2, whatever the means a of value is equal to plus plus.
So can everyone think about that? Suppose you have an array A of n integers, size n, and they are in the range of 0 to 1000. N can be very large, say arbitrarily large. Okay. You want to sort them. But once you know they are in the range 0 to 1000, you can say, okay, let me make a single pass through array A, single pass through A. So when you go to any arbitrary AI, that will lie in this range. It will be between 0 to 1000. So why don't you find out how many elements of A are 0, how many are 1, how many are 2, how many are 3, right? That you can do by creating another array, say C count array of size 1001, 0 to 1000, size 1001. So you can say, okay, if AI is 5, I update C5 with 1. So suppose AI is 5, so that means what I will do, so C5 will be plus 1. If AI is 0 and AI is 0, I'll update C0 as plus 1. That means I found one more element with a value 0. I found one more element with a value 5, one more element with a value 1000, like that. So every AI, you just update one of this C. So for every AI, how much time you take? Constant time. Because you know what is the value of AI? You take that C, this is 5, you take C5 and increment that by 1. So what you are doing? C of AI plus plus. That's all. That's the only thing you're doing. So for I is equal to 1 to n, so C is already initialized, C of AI plus plus. That's all. And you do that for the n elements. So now you know in C array how many times 0 occurred in A, how many times 1 occurred, up to 1000. You know that. Then how can you sort it? How can you sort A now?
Print I ci times. That's
Print it.
That's all. So now you say for I is equal to 1 to say 1000 or 0 to 1000, print I ci times. Okay, you will write in the algorithm, but yeah. So overall, there are only n elements. So this will take, complexity will be what?
Order of n.
Order n, sir.
Order of n. Yes. So you see, so this very simple idea, but restriction. What is the restriction? They should be all integers. Yes, you say, okay, they are all integers. The range is known to you. And in general, this will work if the range is, so range can be arbitrated. Suppose range is 0 to n5. Then
Order of n to the power by.
so that means range should be order n. Sum 0 to k minus 1, where k is order n. As long as range is order n, I can do this in order n. O(n) time, this will take order k. K is the range. And this printing, overall printing will take order n time. O(n) for all values. So this comes out to be order n plus k. Order n plus k. So as long as k is order n, I can have an sorting algorithm that takes O(n) time.
So should the k less than order n or something?
No, k order n is fine. If k is order n, that is fine. You will get order n plus k. Hmm?
If n is 10 to the power 6 where k is 1000, then we cannot call it. Right.
Tell again.
So if the range is 0 to 1000 and we have 10 to the power 6 elements to be sorted.
Hmm. So k is
Here
1000, n is 10 to the 6. So k is order n.
root n.
No, see, n is also order n. So
Yes.
as long as k is of the order of n or less than that is always good for you. Okay. So even if k goes to order n, you're fine. You can get an order n sorting algorithm. But if k goes beyond order n, say order n log n or order n square, then you cannot. At least by the simple way we discussed, the simple algorithm we discussed. So, okay, so I think it's time for today. What are the main ideas? If you do comparison-based sorting, you cannot do better than O(n) log n. We proved the lower bound. And that applies for any way you can think about sorting using comparison solving. And then we said, okay, if you want to use more ideas with some more restrictions on the possible input, you may be able to do better. Like here we saw a simple example where by using the range of the values, if the range is order n, I can get an order n times sorting algorithm, linear time sorting. This is also called counting sort, but we will discuss counting sort in detail next time. There are few more nuances about counting sort that I have not discussed here. But yeah, that is a general idea. But there are some more things that we need to know about counting sort. Okay. So this is what we will do on Friday. So tomorrow, you know, is a holiday due to Diwali. So yeah, wish you all the best. Happy Diwali, and then we will meet on Friday 11. Okay. So 11, we will continue from here. We will have tutorial on hash tables. And you have already got the email that your lab will be on Sunday morning, right? 9 a.m. I hope
Sir?
that is all. Yes.
Sir, regarding the upcoming lab, sir, could you please extend the deadline by 1 hour, because it was initially scheduled on 6th and I shifted the plans from 6th to 7th. So if it is extended by just 1 hour, then I can attend the plans on 7th and still be able to do the lab.
So what do you mean? So what is the time that was told to
Yeah.
you?
9 to 12:30. So if it is possible, could you please extend it to could you please make it 9 to 1:30 instead?
Okay, 9 to 1:30 is what you want.
Yes, sir. It would be very helpful, sir.
Sure. Anybody else has a problem with that? Sure. 9 to 1:30. Okay.
Thank you, sir.
Okay then. So yeah, I will see you on Friday then.
Thank you, sir.
Thank you, sir.
Thank you, sir.